In this lecture, we're going to look at reaction mechanisms and the rate limiting step. But before we begin with this from a chemical point of view, I'd like to first describe what a mechanism is. Now, a mechanism is a series of steps that accomplish some goal. In your life, you can probably imagine many different mechanisms in place where, in order to accomplish one specific thing, you have to go through a series of other things before you can arrive at the end result. I'd like to relate this to you in terms of an uncle of mine who was actually a baker. Now, my uncle would have to, as the first matter of his day, would have to get up at about 4 o'clock in the morning. It was necessary for him to get up that early because of all of the things that he had facing him during the day. The next thing that he would do is he would get to work and he would mix up the dough that he was going to use and bake as part of his bread making process. The next step was to allow the dough to rise, followed by the baking process, and eventually ending with the packaging and the selling of the bread that he had prepared. This is, of course, greatly simplified. There were a lot of other things in his day, I'm sure, but what I like about this particular mechanism, this series of steps, is that it demonstrates there are some things that are in our control, and then there are some things that are not in our control. In this process, the dough rising and the dough baking are two processes, two steps, that are outside of the control of the baker. These actually require a fixed amount of time and cannot be speeded up, really. You have to wait for the bread to rise at its own rate, and then you have to put it into the oven for the 45 to 60 minutes, and there's really nothing that you can do about it. These steps are what we call rate limiting steps. And these are steps that we have really no control over. A rate limiting step is the slowest step in the mechanism. Or in this case, we have two slowest steps. And the rate limiting steps determine the speed of the mechanism. Okay, so an important part of any mechanism is that you need to be able to identify the rate limiting step, because it's the rate limiting steps that really affect how fast something is going to occur. Okay, now let's put this into a chemical context. That's mechanisms in general. Now what we're going to do is we're going to look at reaction mechanisms. And reaction mechanisms have to do with chemical settings. A reaction mechanism is a series of steps, and these steps that I'm going to refer to are known as elementary reactions. A series of elementary reactions, or steps if you prefer, we'll put that in parentheses here, a series of steps, okay, that somehow sum up, they add up to an overall reaction. Up to this point in your chemistry education, you've looked at many different chemical reactions. And we've done things with stoichiometry and grams to mole conversions and everything else. We looked at these reactions as if they are some sort of recipe, and indeed they can be used in that way. But oftentimes what goes on behind the scenes in an actual chemical context are a series of reactions that are hidden from view. Yes, they accomplish what we see and what we expect from the overall reaction, but behind the scenes there's more going on than what the balanced chemical reaction might actually suggest. So we're going to be looking at reaction mechanisms, a series of elementary reactions that add up to an overall reaction, and then we're going to be evaluating them to see whether or not these mechanisms are reasonable or not. Now, whether or not a reaction mechanism is reasonable or not depends upon the results of the following tests. And so we'll just call this tests of reaction mechanisms. And we'll learn how to apply these tests and decide whether or not the reaction mechanism is reasonable or not based upon the results of these three tests. And test number one is that each elementary reaction must be reasonable. Now, how is this possible? How is it possible for a reaction to be reasonable or not? We certainly don't reason with these reactions or have arguments with them. No, reasonable means, is it likely? Is it likely? Is it probable in this case? Now, there are some reactions that are more reasonable or likely than others. For example, we could consider a unimolecular reaction. A unimolecular reaction is really a decomposition reaction where some molecule decomposes into other pieces, all right? Decomposes. This is something that can actually happen. A molecule can absorb a photon of light and spontaneously break up into separate pieces. Unimolecular reactions are quite likely and are reasonable. It's reasonable to think that a unimolecular reaction could occur. Another possible reaction would be the bimolecular reaction. Here, the prefix bi refers to two things. And is it likely that two molecules might collide with one another in some way to produce something else? And of course it is. We've talked about effective collisions in the past, and an effective collision has two molecules colliding into one another with the right orientation and enough kinetic energy for change to occur, and we would get some products as a result of this. This too is a reasonable thing to imagine. Collisions happen. However, if we continue this process and think about the trimolecular possibility, now we're talking about a crash between three molecules at exactly the same time with exactly the right position and orientation. This is now, we're now reaching into an improbable event. Having three things collide at exactly the right time and with exactly the right orientation is really very unlikely, and therefore isn't reasonable. As we evaluate reaction mechanisms, we're going to make sure that each elementary reaction that we observe is either unimolecular, bimolecular. However, trimoleculars and tetramoleculars and anything else requiring more particles than two are going to be considered unlikely and therefore not reasonable from the point of view of an elementary reaction. That's test number one. Test number two. Test number two asks us to combine the elementary reactions and to evaluate the end result. The combined elementary reactions they must reproduce the experimental overall reaction. This is just a fancy way of saying that when we add up all of the steps, the effect of all steps when considered collectively, all together, must be the end result that we were hoping to achieve at the very beginning. And again, an example will probably help demonstrate this to you. And so we'll look at an example here shortly. So that's test number 2. And test number 3 tells us that the rate law equation predicted by the mechanism must agree with experiment. All mechanisms actually can be manipulated in a way so as to give us what they predict is the rate law equation. If the mechanism's correct, if we really understand what's going on behind the scenes in the mechanism, in the reaction, and we've got the steps correct, why then the rate law equation predicted by the mechanism has to agree with the experimentally observed rate law, and if it doesn't, why something's got to be wrong. All right. Now, it'll help to demonstrate these 3 tests, and again, there are just these 3 tests. If a mechanism passes all 3 steps or all 3 tests, why then we can assume that we've got a mechanism that is likely correct. So, what we need to do is we need to look at these tests in the context of an actual reaction mechanism, and that's what we're going to do next. We're going to take a look at an example. Now, what we're going to be looking at is an example of what I refer to as a type 1 reaction mechanism. This is a term that is not used in the book, but I find it useful to put a name with these sorts of mechanisms so that we can keep track of the subtle differences that exist between type 1 and later type 2 reaction mechanisms. And so this is going to be a type 1 reaction mechanism that we're going to look at first. And what exactly is a type 1 reaction mechanism? Well, it consists of a series of elementary reaction steps. That's true. But here's the important part. Step 1 is observed to be a slow step. And step 2 and all subsequent steps are observed to be fast in comparison. All right, so as we look at this very schematic description of a reaction mechanism, we can identify the rate limiting step simply as the one that is slow. And so the rate limiting step is this one right here. And the rate limiting step, abbreviated RLS, is the step that will determine how fast this reaction goes. Steps 2 and 3 go so fast they're practically blinding. But step 1 is taking its time, and for whatever reasons is a very slow step. The entire process can move no faster than the speed of the slowest step. And in a type 1 reaction mechanism, the slowest step is the first step, followed by fast steps subsequently. Now, let's have a look at an actual reaction that has behind the scenes going on a mechanism. All right, I'm going to call this the experimental result. This is part of our example. It's known from the laboratory, the reaction of interest, otherwise known as the overall reaction, looks something like this. We've got NO2 in its gas phase combining with carbon monoxide in its gas phase, forming nitrogen monoxide and carbon dioxide. This is the reaction of interest. It's considered to be the answer. It's the overall reaction. It can be used to describe the stoichiometry that exists between nitrogen dioxide and carbon monoxide as they react to make these products. It's known. In addition to this, in addition to the overall reaction, we also know the rate law equation. This is, again, an experimental result. something that we would determine while working in the lab. And in this particular case, the rate law equation, also known as an experimental result, tells us that the rate of this reaction is equal to some rate constant K, as is always the case, times the concentration of the nitrogen dioxide gas raised to the second power. Okay, this is all given information. In the lab, we've determined this information, but here's what we suspect. We suspect that what's going on behind the scenes, if we could go in with an atomic microscope and watch the goings-on as this chemistry takes place, we have reason to believe that there's actually a mechanism involved. We believe that there are other things going on that lead to this result, but involve steps. And so we ask ourselves, or perhaps we ask a graduate student, to propose a mechanism. Now, this is a very difficult thing to do. It requires a lot of work in the lab. It requires a lot of thought, and it's certainly not something that I would ask you on an exam. However, we get this result back. Our graduate student friend goes off, thinks about it, does some lab work, thinks about things, and proposes the following mechanism. And so we have elementary reaction, otherwise known as step, number 1. And it's proposed that the first thing that happens is that 2 of these NO2s crash together and form nitrogen monoxide and nitrogen trioxide. I'm leaving the subscripts off just to make this a little bit more reasonable, but these are all gas phase species. Now, our graduate student friend also suggests that she has reasons to believe that the mechanism involves a second step. The second step takes nitrogen trioxide, combines it with carbon monoxide to form nitrogen dioxide and carbon dioxide. Now, these two things have been proposed. It's a proposed mechanism, and our goal will be to decide whether or not this mechanism seems reasonable or not. So we've got some work ahead of ourselves, and we'll be applying those 3 tests that we talked about earlier. Okay, so the only other piece of information that we can add to this, supplied by our graduate student friend and the research that she's done, is that she has identified this first step as the slow step. This is really required information, and we need to know it because the slow step tells us that this is the rate limiting step, and that's really a very important piece of information. Okay, so there's the rate limiting step. She also tells us that she believes the step that follows goes with lightning speed and is therefore not going to affect the speed of the overall mechanism. Then it's our job to decide whether or not this mechanism passes the 3 tests that we were looking at above. Now, the first step, or the first test that we have to apply, we need to apply to each of the elementary reactions respectively. We need to decide, are they uni, bi, tri-molecular reactions, and therefore are they reasonable or not? Let's focus our attention on the elementary reaction number 1. Here what we can see is that it requires that 2 of these NO2s collide with one another. We're showing them grouped together with the 2 there, but really it suggests that 2 NO2s crash into one another, and therefore this is a bimolecular step. And bimolecular steps are reasonable, and therefore I'm going to light that up with a happy face because elementary reaction number 1 has passed this test. Similarly, elementary reaction number 2 clearly involves 2 species and is therefore bimolecular as well. And it passes the first test. So, as we've looked through our elementary reactions, we've identified them both as bimolecular, and therefore we can say that both seem reasonable and likely things to be going on. That was our first test. Now, our second test was to look at the combination of all of these reactions and make sure that they sum up, that they represent the overall process, which is up here, the final answer, the experimentally observed, correctly balanced overall reaction. So to do that, what we're going to have to do is we're going to have to add up all of these reactions, which is really a very simple and straightforward thing to do. What we must do is just list everything that's a reactant on the reactant side and everything that's a product on the product side. And I'm going to do that beginning with the reactants coming from elementary reaction number 1, where we had 2 of the NO2s. And while I'm at it, I'm going to check those things off just to make sure I don't miss any things or double count something. Now, that's the only reactant from elementary reaction number 1, but elementary reaction number 2 has the nitrogen trioxide that I need to account for, as well as the carbon monoxide that appears also as a reactant, and I'll check those off as well. That's it for the reactants. We can then move on to the products, and the products coming from elementary reaction number 1, we have NO and NO3. Okay, check those off. And we have NO2, and we have CO2. So we've got all of the reactants on the reactant side, all of the products on the product side, and now what we need to do is we need to simplify this. We've got some redundancy. In the spirit of algebra, things that occur both on the left and on the right can be canceled out. And so you'll see that NO3 here and NO3 on the right both appear and therefore can simply be omitted from the problem. A little bit more simplification, though, we also have NO2 appearing once on the right and twice on the left, and so I'm going to cross out the 2 and rewrite it as a 1. And at that point, I think we've simplified as best we can, and we can rewrite the answer as the NO2 that's left over combining with the carbon monoxide to produce the nitrogen monoxide and the carbon dioxide. And this actually agrees with the overall reaction that we were given above. And so since the combination of the 2 elementary reactions in this way agrees with the overall reaction that we were given at the beginning, why we can say that this mechanism has passed test number 2. All right, so far so good. The only other thing that I'd like to add here in regards to test number 2 is that we noticed that NO3 in this reaction disappeared from view. NO3 is actually an example of a reaction intermediate. The word intermediate suggests something that's produced along the way, something that's produced and then goes away. A reaction intermediate is both produced and consumed by the mechanism. A reaction intermediate does not appear in the overall reaction. Now, it is possible in experimental studies to detect the presence of a reaction intermediate. They don't exist for very long. They come and they go. Step 1 produces a little bit of NO3, and step 2 uses it up very quickly. An intermediate has only a very brief lifetime in the chemical mixture. High-speed lasers, however, can be used to detect the presence of a reaction intermediate, and in fact provide great experimental evidence for the correct reaction mechanism. If you make a proposal for the reaction mechanism that involves the production and the consumption of NO3, and you can't detect it experimentally with the right equipment, why, you may very well be on the wrong track, and your mechanism may be incorrect. Reaction intermediates are produced and consumed by a mechanism but do not appear in the overall reaction mechanism. All right. Well, so far our reaction mechanism has been doing just fine. The last thing that we need to do is we need to evaluate the mechanism in terms of the predicted reaction rate equation. So I'll just rewrite that here and suggest that we need to derive the mechanism's rate equation. And this is actually something that's quite easy to do. What you need to do is be sure that you've identified the rate-limiting step, the elementary reaction that goes very, very slow. I'm going to rewrite it here so that we've got it to look at. Our rate-limiting step involved the nitrogen dioxides colliding with one another to form the intermediate NO3 and the NO. It was listed as the slowest step, and therefore the rate-limiting step. All right. To derive the rate equation from the rate-limiting step is really quite simple. All you have to do is begin by saying that the rate is going to be equal to a reaction rate constant. This is the standard formula for the general rate equation. And then we need to include the concentration of the reactant. We only use the concentrations of the reactants. We will not be using the concentrations of the products in any way, shape, or form. At this point, we've just about got it complete. However, there's one additional piece of information. For elementary reactions, it is possible to use the coefficient that stands out before the reactant as the exponent in the rate equation. And so the rate equation, as predicted by the mechanism, refers to the rate-limiting step, which I've outlined for you here, and uses the concentrations of the reactants, in this case a single reactant, NO2, and we raise it to the second power, because there's a coefficient of 2 out in front of the NO2. The last thing that we do is we compare it to the experimental result, which I listed at the very beginning of the problem, and we see that they are the same. Our mechanism predicts the same rate equation as was observed experimentally, and thus our mechanism has now passed the third and last test, and we can conclude that this mechanism is reasonable and likely to be correct.